Imagine a corporate network, like completely collapsing, millions of dollars just vanishing from ledger databases, or the logistical infrastructure of a whole city grinding to an absolute halt.
Right.
And here's the kicker, right? It is almost never because of some cinematic mastermind sitting in a dark room in a hoodie, typing 1 million words a minute.
No neon code reflecting in their sunglasses.
Exactly. The reality of a catastrophic cyber failure is just, well, it's far more mundane, and honestly, it's far more terrifying.
Oh, absolutely. It's usually something incredibly simple.
Yeah, like it happens because a programmer 20 years ago wanted to save a few bytes of memory by typing 98 instead of 1998.
Yeah.
Or, picture a state-of-the-art enterprise firewall, a multi-million-dollar appliance, failing today simply because a tired developer missed a single tiny closing parenthesis. Just one syntactical error buried deep in 50 million lines of code.
It is a sobering realization, honestly, for anyone entering this field.
I mean, it has to be.
Yeah, because our entire digital world, all of this massive infrastructure we rely on, it just balances on this incredibly fragile edge of basic human syntax and historical hardware constraints, really.
Before we unpack the actual mechanics of how a microscopic typo turns into a catastrophic vulnerability, I want to take a quick second to speak directly to you listening right now.
Make sure you're paying attention here.
Right. If you are serious about your career trajectory in MIS, CIS, or IT, make sure you hit that subscribe button. You want to stay connected so you never miss the insider tips and technical breakdowns that could one day, well, save your network.
And honestly, save your career when things inevitably go sideways.
Exactly. Also, be sure to check out the description below this deep dive for access to some really valuable resources we've linked for you.
Highly recommend checking those out.
So getting back to it, welcome to the deep dive. We are operating as independent industry analysts looking closely at how specific educational pathways bridge that massive gap between academic theory and real-world tech demands.
And this is actually our 7th session.
Yep, 7th out of 14. We're analyzing the curriculum from the 4th edition of Hands-on Ethical Hacking and Network Defense by Wilson, Simpson, and Until.
In our last session, Chapter 6, we went really deep into enumeration.
We did. We explored the mechanics of mapping out a target, identifying the open port.
Active services, yeah.
Right, the literal doors and windows of a network. But today, we are crossing a major threshold. We're looking at Chapter 7, which is Programming for Security Professionals.
This is a huge shift in perspective.
It really is.
Okay.
Our mission today, particularly for you students currently navigating Dr. H.Schuessler's Ethical Hacking and Cybersecurity Operations course, or really anyone stepping into an early career IT role, is to understand why you cannot just be a network operator.
You have to understand the builder's logic.
Exactly. We are learning how software is built, so we know exactly the physics of how it breaks.
Right, because moving from network enumeration to software architecture, it's a monumental shift. If your job is to test a system as an ethical hacker, the days of viewing software as a magical black box are over.
Where data goes in, magic happens, and a result comes out.
Exactly. You must understand the gears turning inside the compiler.
Well, I want to push on that mindset shift right out of the gate. Why does a network defender, someone whose job is ostensibly to, configure firewalls, monitor traffic, why do they need to sit down and learn the mechanics of software development?
That's a great question.
Isn't there a hard line between the software engineering department and the security operations center?
So that hard line you just described, that is the traditional way of thinking. And it is the exact structural flaw that has left so many legacy systems fundamentally vulnerable today.
Really? Just the separation of those teams?
Absolutely. The flaw goes all the way back to how we historically educate computer scientists versus how we educate IT professionals. The curriculum points out a pretty harsh reality here. Traditional computer science degrees just do not historically teach programming with adversarial security in mind. Students are evaluated on whether a program compiles, right? Whether it executes efficiently, whether the UI is responsive. Security, in that classical model, is completely an afterthought.
It's just treated as a perimeter issue.
Exactly. It's something slapped onto the software by a completely different team after the code is already compiled and deployed.
I always look at it like constructing a massive high-tech bank.
Oh, that's a good analogy.
Right. The architects and engineers focus on putting in the imported marble floors, designing the teller windows so they're super fast, filling the vault with cash, and then and only then, right before they open the doors to the public, someone looks around and says, wait, maybe we should hire a security guard for the front door.
That is highly accurate.
Yeah.
And the problem is, when you just slap a guard at the front door of a poorly designed building, a sophisticated bank robber doesn't try to fight the guard.
Right. They bypass the front door entirely.
Exactly. They find a loose brick in the foundation. Or they realize the HVAC system connects directly into the vault. They bypass the perimeter security because the security just wasn't integrated into the core architecture of the building itself.
Which brings us to this massive critical shift in the modern tech industry that the curriculum highlights, the move towards SecDevOps.
Yes, security development and operations.
We hear the term DevOps thrown around constantly, to describe agile software deployment, but injecting that sec at the front fundamentally changes the equation, doesn't it?
It's an aggressive cultural and technical movement. Instead of the old waterfall model,
where developers write the code in a silo.
Right. They write it in a silo, pass it over the wall to operations to deploy, and then security scrambles at the very end to try and patch the inevitable holes. SecDevOps demands a unified pipeline.
So security is there from day one.
Day one. It requires baking security into the code base from the very first commit. It's about understanding the threat model during the design phase, writing exploit-resistant code, and automating security testing right alongside your functional testing.
And if we want to understand the historical cost of ignoring that long-term operational reality during development, the source material brings up the ultimate cautionary tale. We touched on it earlier, the Y2K bug.
The Millennium Bug. It's the perfect historical lens for understanding development trade-offs.
Yeah, because it wasn't just that programmers in the 70s were short-sighted or lazy, right? It was an actual economic hardware constraint.
Exactly. In the 60s and 70s, computer memory wasn't silicon chips. It was often magnetic core memory.
Wow, magnetic core.
Yeah, physically massive and incredibly expensive. We are talking about literal dollars per byte. Every single character a program stored had a tangible financial cost.
So to save memory, they made a very rational economic decision at the time.
They abbreviated 4-digit years into 2 digits. 1975 became 75. 1990 became 90.
Which makes perfect sense if you're a developer optimizing a mainframe database and you assume your code is going to be retired in 5 years anyway.
Right, but they failed to account for the operations side of the future. The software outlived the hardware.
By decades in some cases.
Exactly. When the year 2000 approached, the logic of the code dictated that 00 came after 99. But the systems couldn't differentiate if 00 meant the year 2000 or the year 1900.
And because leap year calculations rely on century divisibility, a lot of software simply did not account for the extra day in February 2000.
Yes. It was a basic logic error, born of a hardware constraint, written into millions of programs globally.
It required billions of dollars to fix, didn't it?
Billions. Rewriting millions of lines of COBOL and C, just massive global overhauls to fix it, before the systems essentially time-traveled backwards and crashed financial sectors.
So, if bad programming, or even just economically constrained programming from decades ago, is the root of the problem, this raises a very intimidating question for you listening right now.
It does.
If you were an early career professional stepping into a massive corporate enterprise today, how do you even begin to audit a system? The sources explicitly note that an operating system like Windows 10 has over 50 million lines of code.
50 million?
50 million. How do you defend a surface area that massive?
Well, you have to understand the scale of the battlefield using industry metrics. And the software engineering standard, which is quite sobering for a security professional to learn, is that there are typically 10 to 15 bugs for every 1,000 lines of production code.
Wait, let me do the math on that. 10 bugs for every 1,000 lines.
Yes. Now, the material notes that a flagship OS like Windows 10 or a core Linux kernel, because of rigorous automated testing and massive engineering budgets, they actually have a significantly lower bug density than the industry average.
Okay, well, that's good.
But let's apply the math anyway. Even if Microsoft or Linux contributors are vastly better than average, let's say they only have 1 bug per 1,000 lines.
Okay.
Across 50 million lines of code, you are still looking at 50,000 microscopic vulnerabilities.
Wow.
50,000 logical errors, race conditions, or memory leaks just waiting for the exact right adversarial input to break the system.
That is a staggering number. it makes the defender's job sound mathematically impossible. Like, if I can't read 50 million lines of code in a lifetime, how am I supposed to secure it?
It's not impossible, but it requires you to stop looking at the sheer volume of code and start mastering the fundamental logic that governs the machine.
The underlying structure.
Exactly. You don't need to read every line. You need to understand the architectural building blocks that make up every single one of those lines. This is where the curriculum brilliantly distills the complexity of programming into a foundational acronym.
The BLT.
The BLT, branching, looping, and testing.
So if we strip away all the complex syntax, the object-oriented architecture, the cloud integrations, all the APIs at the bare metal, CPU level, every software program is essentially just doing those three things, right?
At the assembly level, yes.
Yeah.
Every programming language, whether it's running a basic web calculator, a deep learning algorithm, or the guidance system of a ballistic missile, it relies on these fundamental mechanisms.
So let's start with branching.
Right. In programming, code execution typically flows linearly top to bottom. Branching is the mechanism of altering that flow. It's the program deciding, based on a condition, to jump from one area of memory to an entirely different set of instructions.
I want to elevate this past a simple choose-your-own-adventure analogy. Think of branching in software like a physical bank heist where the robbers approach the main vault. The plan branches based on environmental conditions.
Okay, I follow.
If they check the vault door and the time lock is active, the logic branches. They abandon the main vault and jump their execution path to the safety deposit boxes. But if the time lock is false, they branch to a different execution path, blowing the vault. The execution jumps based on state.
That is a great way to visualize it. At the hardware level, this is literally the CPU executing a JMP, or jump instruction, to move the instruction pointer to a new memory address.
And next we have looping.
Yes, looping. Computers fundamentally are incredibly fast, but they possess zero intuition. They are merely highly efficient at executing repetitive tasks millions of times per second without degradation.
So looping is the structural logic that instructs the computer to perform a block of code over and over again.
Exactly. But a loop without a brake pedal is disastrous.
Which brings us to testing.
Right. Testing is what stops the loop from running infinitely and consuming all system resources, which is a classic denial of service condition.
Just freezing the machine entirely.
Yep. Testing evaluates a specific condition. It looks at a variable or a state and returns a Boolean value, either true or false. A loop will continue to iterate, checking that testing condition upon every single cycle.
And it will only break the loop and pass the execution flow back to the main program when the testing condition returns a specific required value.
Exactly. So connecting this back to the SecDevOps mindset, if you're an ethical hacker, you aren't just looking for a typo. You are specifically hunting for where the BLT breaks down in the logic.
You're looking for a loop that processes user input but lacks a proper test for string length, so it runs out of bounds and crashes the server.
Or you're looking for a branch condition that can be maliciously tricked into jumping execution to a piece of injected shellcode instead of the legitimate application logic.
That is the essence of vulnerability research. But it's important to note that before a developer even writes the BLT logic into a specific language syntax, there is a crucial architectural step that is often overlooked in rushed environments.
Oh, absolutely. Skipping this step practically guarantees a logical bug later. You have to start with an algorithm mapped out through pseudocode.
Let's clarify that term, because algorithm has been totally hijacked by popular culture. When people hear algorithm today, they think of like the mysterious black box that decides what viral videos show up on their social media feed.
Right, the recommendation algorithm. But in computer science, it means something much more fundamental. An algorithm is simply the finite, defined sequence of steps required to solve a specific problem or perform a computation.
It's the raw mathematical logic of the solution before it's ever translated into a specific computer language like C or Python.
Then pseudocode is the bridge between human thought and compiler syntax. Pseudocode is an informal, English-like structural language used to map out that algorithm.
It allows the software engineer to structure the logic without getting bogged down to the exact placement of semicolons or brackets.
It's the architectural blueprint,
which flows naturally into the concept of code documentation. The material heavily emphasizes adding extensive comments to your code base to explain what the logic is doing. It mentions standards like JavaDoc.
Yes, extremely important.
Now, from an academic standpoint, I know students constantly complain about commenting their code. It feels tedious when you just want to get the program running.
It always feels like a chore.
Right. But let's look at this from a security perspective. If you are reverse engineering a legacy system, isn't a massive program without documentation? Essentially like handing a bomb squad a defusal manual where all the paragraphs are redacted.
The nightmare.
If you're an attacker trying to find a vulnerability, poorly documented code that the original developers don't even understand anymore, that's your best friend, isn't it?
It absolutely is the attacker's best friend. This is a massive issue in enterprise environments. We call it technical debt. A brilliant engineer writes a highly complex, hyper-optimized block of code, but leaves zero comments explaining the logic.
And then 2 years later, that engineer leaves the company.
Exactly. When a bug appears in that module, the new developers cannot understand the execution flow. Because they don't understand the original intended logic of the branches and loops, they are terrified to fix it. Or they implement a patch that breaks something else entirely.
So documentation is not an academic chore.
No, it is a vital security control. It leaves a topographical map of the logic for the next engineer, which makes spotting anomalies, logic flaws, and vulnerabilities infinitely easier.
All right, so we've established the operational mindset of SecDevOps, and we have broken down the abstract logic of the machine, the BLT. Now we need to transition into the actual tools, the languages themselves.
Because you can't defend a house if you don't know what materials it's built from.
Exactly. The deep dive really grounds this transition in the absolute bedrock of modern computing architecture, the C programming language.
It is genuinely impossible to overstate the historical and structural importance of C. It was developed by Dennis Ritchie at Bell Laboratories in 1972. It was designed to be concise, incredibly powerful, and it quite literally built the operating systems that run the modern digital infrastructure today.
The curriculum mentions that initially, early operating systems like UNIX were written entirely in assembly language, which, if you've ever looked at it, seems like an absolute nightmare of complexity.
Oh, assembly language is just a hair's breadth above pure machine code, the raw binary ones and zeros. Assembly uses hexadecimal numbers and rudimentary mnemonic expressions like MOV, ADD, or JMP to directly manipulate CPU registers.
Sounds incredibly tedious.
It is. It's heavily prone to human error, and crucially, it's hardware specific. An assembly program written for an Intel chip will absolutely not run on an ARM chip. Ritchie developed C as a high-level language that offered human-readable syntax, but was still low-level enough to interact directly with the computer's memory and hardware without excessive overhead. It was so effective that the entire UNIX operating system was later rewritten in C.
And eventually, C++ was introduced to add object-oriented enhancements to the language.
Correct.
Here is where the mechanics get really interesting for a security professional. You write this human-readable text, the source code in C, but the CPU processor cannot actually read that text. It needs a translator to turn human logic into machine logic.
That translator is the compiler. This is a critical concept. Programs like the GNU-C compiler or GCC, which comes standard on most Linux distributions, or the Microsoft Visual C++ compiler for Windows environments.
And the compiler's job is an incredibly complex pipeline, right?
Yes. It takes your text-based source code, performs lexical analysis, builds an abstract syntax tree to verify the logic, and finally converts it into raw, executable binary machine code.
And as we noted in the introduction, a compiler is completely, unequivocally unforgiving. It does not guess your intentions.
It is absolutely brutal. This is where syntax becomes paramount. The syntax in a C program must be mathematically exact. If you are missing a single closing parenthesis, or if you forget the mandatory semicolon at the end of a statement, the compiler cannot build the syntax tree.
It just throws a syntax error.
It halts. The program simply will not build. But there's a much more dangerous scenario. What if the syntax is perfectly correct, but the logic is flawed?
Then it compiles successfully, right?
Yes. The compiler will happily build a program with a logical error, producing an executable that compiles cleanly but executes with unpredictable, really dangerous results.
To understand how those logical errors happen, let's walk through the anatomy of a basic C program. Let's look at the Hello World program, which is the universal starting point for basically every programmer.
It's the best way to see the skeleton of the language. In C, you almost always start with an include directive at the very top of the file. For example, #include stdio.h.
And that tells the compiler's preprocessor to load the standard input-output library.
Exactly. This library contains pre-written, highly tested functions that interact with the operating system, like printing text to a monitor or reading input from a keyboard so the developer doesn't have to write raw hardware interaction code from scratch.
And then, below the include directives, you absolutely must define a main function.
Yes, Every single executable C program must contain one and only one main function. It serves as the entry point. When the operating system launches the binary, the execution flow starts at the first instruction inside main.
And to define the boundaries of that function, C utilizes braces, the curly brackets.
Right. Everything between those braces is the block of code belonging to that function. The compiler relies entirely on those braces to understand scope and structure.
And inside those braces, we get to variables and operators. Now, looking at C compared to modern scripting languages, it feels like C forces you to micromanage the hardware.
Very much so.
You can't just create a variable. You have to declare to the compiler exactly what type of data that variable will hold, and by extension, exactly how many bytes of memory the system needs to reserve for it.
That is the defining characteristic of strongly typed, statically typed languages. You have to be explicit. If you want a variable to hold a whole number, you declare it as an integer using int, which tells the system to reserve typically 4 bytes of memory.
And if it's a real number requiring a decimal point,
you declare it as a float or double, which requires more memory for precision. A single character is a char, taking 1 byte. You can also declare a const, which is a constant variable holding a value that the compiler will protect from being modified during runtime.
Which is perfect for something like a fixed mathematical value or a tax rate.
Exactly.
And if you want the program to display these variables back to the user, you can't just tell it to print the variable name. You have to use conversion specifiers.
Right. If you use the print function, you have to format the output string and tell the compiler exactly how to translate the binary memory back into human-readable text. You use %d for a decimal integer, %s for a string of characters. You are literally holding the computer's hand at the memory level.
And then we manipulate those variables using operators. We all understand basic mathematical operators like addition and subtraction, but for a security analyst looking at code logic, the relational and logical operators are where the critical decisions, the testing phase of our BLT, actually happen.
Relational operators compare 2 values in memory. To check if variable A is greater than variable B, you use the greater than symbol. But the most critical operator to understand, and the source of countless bugs, is equality.
To check if A is exactly equal to B, you use a double equal sign.
Yes.
Let's expand on why that is so critical. Why is confusing a single equals with a double equals such a massive vulnerability?
Because at the CPU level, they do entirely different things. A single equal sign is an assignment operator. It takes a value and writes it into memory, overwriting whatever was there. The double equals is a comparison operator. It simply compares 2 memory addresses and returns true or false, altering nothing.
Oh, I see where this is going.
Yeah. If a developer accidentally writes if user role admin with a single equals, they aren't testing if the user is an admin. They're actively overwriting the user's role in memory to become an admin.
And the condition will evaluate as true, granting immediate unauthorized access.
Exactly. It's a 1-character typo that completely compromises an authentication system.
That is exactly the kind of microscopic syntax detail that breaks global infrastructure. And logical operators allow you to chain these dangerous conditions together.
Yes. The double ampersand symbol represents the logical A and D. Both conditions must evaluate to true for the branch to execute. The double pipe symbol represents the logical OR. Only one condition needs to be true. And the exclamation mark is the not operator. It negates a condition, so exclamation equals means not equal to.
So if we synthesize all of this, the exact syntax, the explicit memory typing, the logical operators, how does C construct the looping mechanism of our BLT?
C provides 3 primary structures for looping, and the mechanical differences between them are vital for a security auditor to understand. The first is the while loop. The defining feature of a while loop is that it evaluates the testing condition before it executes the code block.
So if a test condition evaluates to false at the very beginning, the execution pointer jumps right past the loop. The code inside never runs, not even once.
Exactly. The second structure is the do while loop. This is the inverse. It executes the code block first, and then evaluates the test condition to determine if it should jump back up and repeat.
Therefore, the code inside a do loop is mathematically guaranteed to execute at least one time, regardless of the system state.
Yep.
I can easily see how a vulnerability could occur if a developer accidentally used a do loop for a sensitive data access routine instead of a while loop. The system would process the data once before ever checking if the user actually had the authorization to see it.
It is a really common logic flaw. And the third structure is the for loop. This is utilized when the developer knows in advance exactly how many iterations are required. The for loop is highly structured. It contains 3 distinct expressions in its setup.
The initialization of a counter variable, the condition that must remain true, and the incrementation step.
Right.
Looking at C from a systems architecture perspective, it is incredibly granular. It forces the developer to manually manage the computer's memory allocation. And for a security professional, this is the ultimate payoff. Because if you understand C, you understand the exact physical mechanics of how memory works.
You understand the stack, the heap, and pointers.
Which means you understand exactly how the most devastating latency attack in cybersecurity operates, the buffer overflow.
That is the crucial takeaway from this entire chapter. C does not hold your hand. It assumes the programmer knows what they're doing.
Which is a bold assumption.
Very bold. If a programmer allocates a buffer in memory, say, an array designed to hold a 10-character password, but they fail to write the proper BLT logic to restrict user input to exactly 10 characters, C will not stop a malicious user from inputting 500 characters.
It will just keep writing.
It will dutifully write those first 10 characters into the buffer, and then it will just keep writing the remaining 490 characters into the adjacent memory addresses on the stack.
And those adjacent memory addresses aren't empty. They hold critical execution data, like the return instruction pointer, which tells the CPU where to jump next after the function finishes.
Precisely. In a buffer overflow attack, the attacker purposefully inputs a massive string of data designed to overflow the buffer and overwrite that return instruction pointer. They overwrite it with a memory address that points directly to their own malicious payload, their shell code, which they also smuggled in through the overflow.
When the function finishes, the CPU reads the overwritten pointer, jumps to the malicious code, and executes it with full system privileges.
It's devastating. And if you don't know how to read C, you cannot audit a code base to find that missing input validation desk.
You have to master the foundation. But let's shift our perspective. That is the deep back-end logic, interacting directly with the metal. But to truly defend a modern enterprise network, you cannot just live in the back-end memory stack.
No, you can't.
You have to secure the front door where the users actually interact with the system. And that means transitioning our focus from back-end programming and memory management to front-end structural formatting. Let's talk about the language of the web, HTML.
HTML is the foundational language of the internet. It provides the skeletal structure for virtually every web page and web application you interact with daily. However, there is a very persistent, fundamental misconception that we need to address immediately for anyone entering the IT field.
What's that?
HTML is fundamentally not a programming language.
Because it doesn't possess a BLT.
Exactly. HTML cannot branch based on conditions, it cannot loop over data arrays, and it cannot evaluate mathematical tests. HTML stands for Hypertext Markup Language. It is strictly a formatting language.
Its entire purpose is to instruct the user's web browser on how to structurally display text, render images, and format hyperlinks.
It achieves this using tags, which are keywords enclosed within the less than and greater than angle brackets. And crucially, almost every structural tag requires a corresponding closing tag, denoted by a /, to tell the browser where the formatting ends.
So mechanically, if I want to display a paragraph of text, I open it with a P tag, type the text, and close the block with a P tag.
Right.
And unlike C, which requires a complex compiler to translate code into binary, HTML is interpreted sequentially by the browser engine. Anyone can write it. You don't need a compiler. You just need a basic text editor like Windows Notepad, save the file with an .html extension, and the browser will render it.
Furthermore, you can inspect the HTML source code of any public web page simply by right-clicking and selecting View Page Source.
Yes, the transparency of HTML is a core feature of the open web. So let me challenge the necessity of this for a security operator. If HTML is strictly structural formatting, if it lacks logic, how dangerous can it really be?
It can be incredibly dangerous.
But if C is the structural steel and the vault doors of our bank, isn't HTML just the paint on the walls? Why does a student enrolled in a rigorous cybersecurity operations course need to dedicate time to studying web formatting?
It is the paint on the walls, yes. But that paint can be manipulated to camouflage incredibly dangerous trapdoors. Because HTML is the ubiquitous front door to the application, it is the primary delivery vector for some of the most pervasive and devastating client-side attacks on the web.
So an ethical hacker or an SOC analyst responding to an alert must know how to read raw HTML source code fluidly.
They have to recognize the mechanical indicators of compromise.
What specific mechanisms are we looking for when auditing HTML?
On a basic level, you're looking for manipulated anchor tags, tags that define hyperlinks. where the visible text says, click here to reset your bank password, but the href attribute is pointing to a malicious type-squatted phishing domain.
Right.
But the far more complex and dangerous threat is understanding how HTML structurally interacts with the actual programming languages that are embedded within it, specifically JavaScript.
Because modern HTML5 allows developers to embed logical scripts directly inside the formatting tags.
Exactly. The browser reads the HTML document sequentially to build what is called the Document Object Model, or the DOM. When the browser parser encounters a script tag, it pauses rendering the HTML and executes the logic inside that tag.
Okay.
If a web application has a poorly secured input field, say a forum comment section or a user profile description that fails to sanitize the input, an attacker can submit a comment that contains raw HTML script tags wrapped around malicious JavaScript.
This is the mechanism for cross-site scripting, or XSS.
Precisely. The server saves that malicious comment in the database. When a legitimate user visits that page later, the server sends the HTML containing the attacker's script. The victim's browser parser reads the page, sees the injected script tags, assumes they are a legitimate part of the website structure, and executes the malicious code within the trusted context of the user session.
Wow. And that script can then steal the user session cookies or force their browser to perform actions without their consent.
Yes. If you do not intimately understand HTML syntax, you will never be able to parse a weblog and spot the missing closing tag or the improperly escaped input field that allowed the DOM to be hijacked. You have to know what the baseline of normal looks like to identify the anomaly.
That makes perfect sense. So HTML is the structural front door, C is the deep architectural foundation. But as a security professional operating in the real world, you are rarely writing operating systems from scratch, and you aren't just designing web pages.
Right, you're usually connecting things.
Exactly. You are constantly parsing massive firewall logs, automating penetration testing tools, and connecting disparate security systems together. You need power tools. You need fast, agile languages that do not require the strict, heavy compilation process of C.
Scripting languages.
This pushes us naturally into the realm of scripting languages. Let's look at the tools highlighted in the text. Perl and Python.
Scripting languages are really the lifeblood of security operations. They allow an analyst or a hacker to write functional programs that are interpreted by the system on the fly, line by line, rather than needing to be compiled into a static binary executable beforehand.
Which allows for rapid prototyping and automation.
Let's start with the historical heavyweight, Perl.
Perl stands for Practical Extraction and Report Language.
Developed by Larry Wall in 1987. It was designed specifically for text processing and system administration. It is incredibly powerful, highly flexible, and it runs natively on almost any platform. In fact, if you spin up almost any Unix or Linux-based OS today, Perl is likely installed right out of the box.
The curriculum mentions that Perl has a unique, almost dual nature within the cybersecurity ecosystem.
It does because of its core strengths. Because Perl is unmatched at parsing complex text strings using regular expressions, and because it handles network socket communication very efficiently, malicious actors historically utilized Perl heavily to develop automated exploit scripts, rapid port scanners, and the command and control logic for botnets.
But conversely, network defenders rely on Perl for the exact same mechanical reasons.
Exactly. They write Perl scripts to automate repetitive security tasks, to ingest and parse millions of lines of syslog data looking for the specific text signatures of an intrusion attempt, and to automate incident response actions.
What does the syntax of Perl look like under the hood? Does it share the brutal, exact syntax requirements of C?
Its syntax is heavily influenced by C, which is why learning C as your foundational language makes picking up Perl much easier. It utilizes the standard BLT structures for loops, while loops, and if statements that function mechanically almost identically to their C counterparts.
Utilizing the same mathematical and logical operators.
Right, but Perl has highly specific quirks. In Perl, every single scalar variable must be prefixed with a $sign. Comment lines, used to document the logic, begin with a hashtag or pound symbol hashtag. When you want to define a custom function, you use the specific keyword sub short for subroutine. And historically, when you call that subroutine, you prefix it with an ampersand symbol.
So it is a highly punctuated, symbol-heavy language.
Extremely. It is notorious for being difficult to read if the developer doesn't write clean code. We often joke that Perl is a write-only language because reading someone else's complex Perl regex can be nearly impossible.
Okay, so that's the veteran language.
Mm-hmm.
But if you walk into any modern security operations center today, or if you look to the tool set of any contemporary penetration tester, The absolute heavyweight champion that dominates the landscape is Python.
Python has fundamentally conquered the security tooling landscape over the last decade. The curriculum notes Python 3.9 as a recent stable release, and like Perl, it is highly portable across different operating systems. It was designed from the ground up with a philosophy of readability and versatility.
And one of the most powerful features for a security tester who is actively engaged in an assessment and needs to test logic on the fly is the Python interactive shell.
We call it the REPL environment: read, evaluate, print, loop. If you simply type Python into your command terminal, you drop into an interactive shell. You can type a line of code, and the Python interpreter immediately reads it, evaluates the logic, prints the output to the screen, and loops back, waiting for your next command.
That is incredibly agile. You don't have to write a full script, save it to a file, compile it, and run it just to test a hypothesis. You can perform quick hexadecimal conversions, test a piece of logic, or use a library to send a single forged network packet directly from the terminal.
It is the ultimate tool for rapid security prototyping. But what truly separates Python from C and Perl mechanically is its unique approach to syntax, specifically how it handles the BLT code blocks.
Right. I want to highlight this because earlier we discussed how C relies entirely on those curly brackets to define where a loop or a function begins and ends. How does Python's interpreter know the boundaries of a function without brackets?
This is the most defining and polarizing characteristic of Python. It enforces structure through strict white space indentation.
I love this structural comparison. Writing in Perl, or C, is like writing a very traditional, heavily punctuated legal document where every clause ends with a clear semicolon and paragraphs are rigidly defined by brackets.
As long as the punctuation is correct, the compiler doesn't care if it's messy.
Right. But Python is more like modern poetry, where the blank physical space on the page literally dictates how the interpreter reads the logic. If you mess up the indentation of a loop in Python, your security script doesn't just look visually disorganized. The interpreter cannot build the syntax tree, and the script fundamentally breaks. Right.
Exactly. In C, you could theoretically write an entire complex program on a single massive line of text as long as every semicolon and bracket is perfectly placed, and the compiler would parse it flawlessly. In Python, if the code block meant to execute inside an if statement is not indented exactly 4 spaces or 1 tab beneath that statement, the interpreter throws an indentation error.
It literally forces developers to write readable, structurally clean code.
Yes.
What about the variables and logic testing? Does it require the dollar signs like Perl?
No special prefix symbols for variables. It uses dynamic typing, so you don't even need to declare int or string like in C. The interpreter infers the type based on the value assigned. You don't use semicolons to terminate lines. For comments, it utilizes the hashtag symbol, similar to Perl.
Okay, so a bit cleaner.
Very much so. To define a function, you use the def keyword, followed by the function name in parentheses. And for conditionals, it uses standard if and else statements, but introduces a highly efficient keyword, else, which stands for else if. It allows developers to chain multiple conditional tests together without creating deeply nested, messy code blocks.
So writing procedural scripts in Python or Perl is phenomenal for automation. You can write a 20-line Python script using the socket library to scan 100 IP addresses for open ports in a matter of seconds.
It's incredibly fast.
But as an analyst looking at the reality of enterprise infrastructure, modern corporate software is not just a collection of standalone procedural scripts running top to bottom. Enterprise applications are incredibly complex.
Oh, massively complex.
They manage massive scale, integrating databases, user interfaces, and cloud services. To handle that level of complexity, the industry transitions to an entirely different architectural paradigm: object-oriented programming, or OOP, and languages like Ruby.
This is a massive conceptual leap. The curriculum rightly points out that mastering OOP requires a fundamental rewiring of how you think about data and logic. It is no longer just writing a procedural list of instructions. Object-oriented programming restructures the very architecture of the code to model real-world entities.
Walk us through the mechanics. How does OOP differ from the procedural C code we discussed earlier?
Well, in procedural C programming, you have data stored in variables, and you write isolated functions that you pass that data into. The data and the logic are separate. OOP binds them together using mechanisms called classes and objects. Think of a class as a structural blueprint or template.
Okay, a blueprint.
It is an encapsulated structure that holds both the raw data called attributes and the specific functions designed to manipulate that data called methods.
The text utilizes a classic C++ example to illustrate this: an employee class.
Right. So you define a blueprint called the employee class. Inside that class definition, you declare variables to hold data like first name, last name, and place of birth. But crucially, you also define the member functions within that class that specifically interact with those variables, like a function to calculate their payroll.
And the object is what materializes when you actually utilize that blueprint in the system memory.
Exactly. The object is a live instance of the class in memory. If you use the employee blueprint to create a specific record for John Doe, that specific instance is the object. And to interact with the data or functions inside that object, you use specific syntax. In C++ lore, you often use the double colon scope resolution operator, so calling employee.getEmp tells the program to execute the specific function that retrieves data encapsulated within that exact class structure.
Now, when we scale this up to enterprise architecture, and we have thousands of different software objects and entirely different servers needing to communicate and share data, we have to introduce APIs, application programming interfaces.
APIs are the connective tissue of the modern internet. They define the exact rules and protocols for how different software components or entirely disparate systems across the globe communicate with each other.
Like when a mobile app requests data from a server.
Yes. When your smartphone's weather application pulls real-time meteorological data from a national server, it is not querying their database directly. It is sending a structured request to their API, which returns a serialized object, usually in JSON format.
The operational advantage is obvious. It enables incredible speed, modularity, and connectivity. It allows microservices to exchange requests and responses in milliseconds, which makes the modern, highly integrated web possible.
But the disadvantage, and this is the double-edged sword that every security professional must understand, is that APIs drastically expand the attack surface of an application.
By design, an API is meant to expose internal data and functions to the outside world.
Exactly. If a developer builds an API that takes a request from a mobile app and pulls an object from the internal database, but fails to implement rigorous authorization tests on the back end, the API simply trusts the request an attacker can manipulate the parameters.
They can request objects they shouldn't have access to?
Which is a vulnerability known as Insecure Direct Object Reference, or IDOR. Or they can inject malicious commands directly into the database through the API payload.
Which perfectly illustrates why understanding OOP architecture and how these complex objects interact is absolutely non-negotiable for a modern defender.
Absolutely.
Which brings us to the final language highlighted in this section, Ruby. And honestly, arguably the most critical reason a student in an ethical hacking course needs to learn the mechanics of Ruby, the Metasploit framework.
Ruby is an incredibly powerful, dynamic, open-source programming language. It is heavily focused on simplicity and productivity, and it is a pure, object-oriented language. Everything in Ruby, even a simple number, is an object. But you are entirely correct. Its paramount significance in this specific cybersecurity curriculum is tied directly to its role as the foundation of Metasploit.
For those who might not have hands-on experience yet, Metasploit is essentially the industry-standard software framework utilized by penetration testers and red teams to develop, test, and execute exploit code against remote targets. And the entire framework is written in Ruby.
Yes. Metasploit contains thousands of pre-built modular exploits for known vulnerabilities across hundreds of platforms. But here is the critical lesson for anyone entering the workforce. To be an effective, highly valued, ethical hacker, you cannot just be a script kiddie.
You can't just run the automated tool.
No, you cannot simply launch a console, search for an exploit, click a button, and hope the default payload works. You must possess the capability to read, understand, and modify the underlying Ruby code within those exploit modules.
So if I am a student in Dr. H.Schuessler's course preparing to enter the professional workforce, I cannot rely on just downloading prepackaged modules off GitHub. I need to understand the OOP principles of Ruby so that I can literally pop the hood on the framework, look at the engine, and rewrite the reverse shell payload code myself to adapt to the specific architecture, the antivirus constraints, and the firewall egress rules of the exact network I am legally contracted to test.
Precisely. In a real-world engagement, a standard, off-the-shelf Metasploit payload will be instantly flagged and blocked by any competent modern endpoint detection and response system.
Because the signature is already known.
Right. You need to know enough Ruby and understand how the exploit class inherits from the framework's core modules to go into the source code and alter the payload's behavior. You might need to change how it allocates memory, alter its encoding to obfuscate the signature, or change the API calls it uses to communicate back to you.
That requires a deep functional understanding of OOP, variables, and the specific syntax of Ruby.
Yes, and when you reach that level, you are no longer just utilizing a tool someone else built. You are actively forging your own custom weaponry to test the defenses.
That is a brilliant encapsulation of the required skill level. Okay, let's take a step back and synthesize everything we have covered in this session, because this has been an incredibly dense journey through the very DNA of computing architecture.
It's a lot to take in.
It is. To truly defend a modern network, and this is a core underlying philosophy we have seen throughout this entire curriculum analysis, you absolutely cannot afford to treat software as a magical black box.
No, you can't.
Whether it is understanding the uncompromising bare metal syntax of C and how a missing bounds check leads directly to a memory stack buffer overflow, or realizing that the structural formatting tags of HTML are the primary vector for injecting cross-site scripting trapdoors into the DOM.
Yep.
Whether you are utilizing the agile interpreted power of Perl and Python to rapidly automate your log parsing and build custom network scanners, or you are diving into the complex object-oriented architecture of Ruby and APIs to customize specific Metasploit payloads to evade detection, mastering the native language of the attacker is the only viable way to engineer truly impenetrable defenses.
It all connects perfectly back to the concept we established at the very beginning of the hour, the mindset shift. SecDevOps. We have to fundamentally stop treating security as a padlock we slap on a broken door right before deployment, and we must start engineering secure, logically sound structures from the very first line of pseudocode.
Think back to the hook that started this deep dive, the Y2K bug born of physical hardware costs, or that single missing syntactical parenthesis that crashes a global server. Today, we didn't just learn that these errors exist in the wild. We explored the deep mechanics of why those tiny syntactical and logical errors cascade through the compiler into the memory stack and become massive vulnerabilities.
Exactly.
We learned how understanding the core BLT logic, branching, looping, and testing, is how we identify those flaws and fix them before the code is ever compiled into production.
Ultimately, the difference between a highly vulnerable enterprise network and a secure one is often simply down to having a defender on the team who understands exactly what happens in the system memory when an array overflows.
Well said. I want to thank you all for joining us on this incredibly detailed deep dive today. Again, if you are serious about leveling up your technical skills and taking ownership of your career path, hit that like button, subscribe to the channel, and please share this session with your colleagues and classmates. Be sure to check the description below for the specific resources, documentation, and tools we mentioned today.
There's a lot of great material down there.
And don't let the learning stop here. Continuously learn. Review the channel for other extensive podcasts, playlists, and videos we have put together analyzing these critical pathways. Specifically, I highly encourage you to check out my Digital Forensics podcast series, where the network and system security deep dives for further context on how these vulnerabilities are investigated after a breach.
This is a constantly and rapidly evolving field. The specific programming languages and the tools will inevitably change over time, but the architectural fundamentals we discussed today remain permanent.
And we are far from done with this textbook. Next week, we are moving on and tackling Chapter 8, Desktop and Server OS Vulnerabilities. We will be taking the foundational programming knowledge we acquired today and applying it directly to understand how massive operating systems fracture and break down under active adversarial pressure. But before we go, we want to leave you with a final complex thought to mull over as you continue your studies.
As we transition rapidly into an era where artificial intelligence and large language models are actively writing more and more of our production code, generating complex scripts and object-oriented algorithms in seconds, who is fundamentally responsible for the bugs?
That's a huge question.
If an AI generates a massive software project with a subtle, hidden logical flaw in the BLT structure, are we inadvertently inheriting an entirely new generation of vulnerabilities hidden deep inside machine-generated algorithms that human engineers never fully audited or understood?
Master the attack, fortify the defense. Until next time, keep your hands on the keys and your network secure.